Okay, so far this is in the whiteboard there shows the summarization of what we explained earlier. So as you can see there, if you talk about a low dark contrast image, the histogram, okay, I just draw the roughly the histogram. So again you can see that I used the R there, and then the y-axis is frequency. So if the histogram occupy that region, okay, I draw it a continuous line. Of course the histogram should be, you have a bar there like in the slide over here, okay, like the one that in the slide there, okay, it should be uh, yep, in bar like this. But in this whiteboard I draw it in continuous line. So just hopefully that you understand that actually should be a bar there represent histogram. So if you find out the histogram is in this form, then this is actually double confirm you that that image is a low dark contrast image. Okay, and then if you find out the histogram is like this, then it's belong to a low bright contrast image. And if you find the histogram occupy a very narrow at the centers, then we cannot say it's a dark or bright. Then it should be, okay, it should be I forget to label it, this one. Okay, this one is this one. So the low contrast image, okay, if you find out that the lines there is very narrow, okay, so for high contrast image, okay, it should be look like this. Okay, meaning that almost all intensity value or intensity level value, intensity value or gray level, gray levels there, gray level values there is occupied, okay, by that image. Okay, I think actually before we learn histogram equalization, you have you should realize that the previous transformation function such as power law transformation function, we are applying it for some image where that image is actually is either belong to low dark contrast image or low bright contrast image. Okay, for example, let's go back to the slide there. Okay, if you realize that in our slide, in our previous slide, okay, okay, for example, yep, how about, yeah, this one. Okay, this one actually is a low bright contrast image because it's very low contrast, and the most of the pixels there, actually the color is belong to bright side. So that's why we call it as a low bright contrast image. Even if you plot the histogram, then you will find that most of the histogram occupy at the bright region or on my right side, okay. So that is that's why I said that instead of uh, okay, one way to improve the low bright contrast image or low dark contrast image, you can use a power law. Okay, if you talk about if the image is with this condition, which is low bright contrast image, you can use a power law, which is the gamma more than 1. Okay, then if you talk about low dark contrast image like this one is also considered as a low dark contrast image, then you can use the power law transformation function where the gamma is less than 1. Okay, so meaning that later why we'll still discuss about this contrast is because the one another alternative uh, operation or another alternative approach that you can use to increase the contrast of the image is by using the method called histogram equalization. Okay, this one we don't expose to you with the image histogram or the histogram of the image is because uh, this approach does not utilize the histogram to formulate or to execute the function, the transformation function. Okay, but histogram equalization, in order for you to generate the transformation function or execute the transformation function, you need the histogram of the image, okay, of the or the image histogram. Okay, don't get confused with that. Okay, same goes to this one. Okay, this one is a low dark contrast image. Okay, you can double confirm by if you want to double confirm, then you need to generate the histogram. You will find out that most of the histogram occupy at the dark region, okay, on your left side there. Okay, let's go back to our discussion earlier. Okay, let's go back to this whiteboard. So if you talk about an ideal high contrast image, okay, this is the okay, let's okay, this is actually is a ideal high contrast image. If you plot the histogram and you find out that it utilize each and every intensity value from 0 to 255, plus the histogram is well and equally distribute, meaning that the frequency there is very fixed and straight line. So that is an ideal high contrast image. Of course, in reality or in practical, it's very hard to achieve ideal high contrast image. But the purpose of why we call this approach, okay, in this video lecture we talk about the histogram equalization. Why the name of that approach is histogram equalization is because we want to improve the contrast of the image. Okay, doesn't matter is it low dark contrast image, low bright contrast image, or low contrast image, or even high contrast image. We want, okay, the objective of histogram equalization, we want this one, okay, we want this one, this one, this one, or this one to, by applying the histogram equalization, okay, it will going towards producing image which this histogram. Okay, that is the main objective of histogram equalization. The process is itself is generating a transformation function that can, from this any condition of these four, 1 2 3 4, it will make or generate some improved image where that image actually is going towards ideal high contrast image where the histogram is equally distributed from 0 to 255 if you talk about the intensity level resolution of 8-bit per pixels. Okay, this is the formula of histogram equalization. Okay, like I said before in early of this video, okay, I rewrite back the equation in my whiteboard there. Okay, this is the formula of histogram equalization. As you can see that we'll still have a transformation function, okay, which is this one. However, for histogram equalization, the transformation function is a cumulative distribution function that represented by this C bracket R, okay, is also known as a CDF. Okay, in your slide there, if you refer to our slide there, they call it cumulative density function, but in our course, let's call it as a cumulative distribution function. Okay, this one is called a cumulative distribution function. Okay, why I changed the name actually is not a problem to call it a cumulative density function, because if you remember, okay, this cumulative distribution function is come from because summation process of, okay, the summation process of your P over here, where this P over here is actually your PDF, or also known as a probability. Okay, probability distribution function. Okay, I just change it from density to distribution is because of we are dealing with a discrete value. Of course, your image is a digital signals, so that's why we are dealing with discrete value. Anything discrete should be If you talk about the probability, okay, you learn probability in your secondary school. If you talk about some discrete event, that is related to probability distribution function. But if you talk about the continuous event, it's related to probability density function. So the density, it's related to analog signal. So that's why now I changed the word there. Instead of using D as a density, I use this D as a distribution. Okay, probability distribution function and cumulative distribution function. Okay, actually there's no problem about that word. Is actually, you can also use a density, because just to differentiate between a discrete and continuous, or analog and digital signals. Okay, so you can see that. Okay, so how to generate a probability distribution function? Okay, this is how you generate the probability distribution function. Okay, forget about this cumulative, because this cumulative operation actually for the purpose of generating the cumulative distribution function. Okay, if you talk about the probability distribution function over here, okay, actually is defined by this thing, where to find the each and every distribution of the probability of each and every values there. Okay, this is the numbers of pixels. Okay, numbers of pixels, and this is the total number of pixels. Okay, this one is total numbers of pixels inside your image. Or this one is a number of pixels where that pixel is number of pixel width. Okay, I forgot to mention the number of pixel width, intensity value equal to your key. Okay, so if your intensity value is 0, which is black, so how many pixel consists of 0 inside the matrix? So then you must have here, and then you must divide by the total of the pixel inside the image. Okay, so again, to generate the PDF there, okay, see, you can see the relations there. To get actually this is, okay, this is your frequency. Okay, because frequency is also known as a number of pixel belong to intensity value equal to 0. Intensity number of pixel with intensity value equal to 1. So you will do that you will do that repetitively until 255 if you talk about intensity level resolution equal to 8 bit. And then that is actually, if you talk about number of pixel with intensity value equal to k, actually inside the histogram actually is actually your frequency, which is your y-axis. So the total number of pixel, that one you can calculate, because of course you should know the sampling resolution. Okay, total number of pixel is actually your sampling resolution, because if you talk about 100 times 100, then it become how many there? 1000. 100 is 100 times 100. So 100 times 100 image. Okay, sorry. 100 times 100 intense spatial resolution, or the size of the image. The size, not the size in the memory, is the size of the matrix. So the size of the matrix actually is a sampling resolution, 100 times 100. So it should be, okay, it's 10 million, or 10k there. Okay, 10k, 10 kilopixels. Okay, so this is the we can consider as your sampling resolution as well, if you want to relate with the previous chapter. So it's not so difficult to count that. So that is why I okay, from here you can see that in order to get this information, of course you need to have the histogram. Okay, so that's why I draw in the previous whiteboard there. Okay, to get my transformation function of histogram equalization is actually equal to my CDF, which is cumulative distribution function, this one. Okay, this one. Okay, this one. Okay, and then cumulative distribution function, to get it you must to do some summations there, summations with summation of probability distribution function. That's why you need PDF, because you want to do a summation of PDF to get a CDF. And then CDF actually is come from my histogram, because the equation to generate the probability distribution function, actually I need this NK, where NK is my frequency, where frequency I can obtain from my histogram. So that's why I said this is the process to generate the transformation function of histogram equalization. Meaning that if you have some condition where the image is low dark contrast image, the histogram should look like this. Okay, and then if you have low bright contrast image, then you have histogram like this. And then if you have a low contrast image, the histogram look like this. So in other words, each and every histogram here is keep vary. It's a difference, meaning that if the image is suffer with a low dark contrast image, this is the histogram. And then of course, by having this type of histogram, the PDF will generate according to this histogram, and you get one type of transformation function. But if you put another image which suffer with low bright contrast image, then the PDF is changing, the CDF is changing, then the transformation is changing. Same goes to the low contrast image like this, because the histogram is keep changing. That's why the transformation function is changing, because of the CDF is keep changing. So that's why I mentioned earlier, the histogram equalization can considered as adaptive approach, because the transformation function is keep changing, depend on the condition or type of image that you want to tackle. Okay, but actually it's good, it's better than the previous one, because if you talk about the power law transformation function, then you need to tune by yourself whether you want to use gamma less than 1 or more than 1. Okay, if you want to tackle low dark contrast image, then you need to use gamma. I also forget that one, should be okay. If you want to tackle a low dark contrast image, yep, this is one, then you need to use a gamma less than 1. If you want to tackle low bright contrast image, you must to use gamma more than 1 actually. So the user need to set by itself. But for histogram equalization, it's more advanced. Okay, that is the advantage of histogram equalization, is an adaptive approach, because regardless what type of low contrast image that your image is suffer with, the system will automatically generate the suitable transformation function for you, because the transformation function is depend on the CDF, and the CDF is depend on the PDF, and the PDF is depend on histogram. Okay,